A black hole might be erasing reality itself. At the heart of modern physics lies a terrifying contradiction called the black hole information paradox, and it threatens to unravel everything we think we know about the cosmos. You will gain a complete understanding of this fundamental crisis, from its shocking origin to the mind-bending theories that could resolve it. We will see how the universe's two most successful rulebooks violently disagree, and whether a dying star's legacy can truly be deleted from existence. Does the fabric of space and time have a permanent memory, or is there a cosmic delete button waiting in the dark? The universe has two rulebooks, and they are written in completely different languages. One book is a meticulous ledger for the impossibly tiny world of atoms and particles. This is quantum mechanics, and its most sacred law is that nothing is ever truly forgotten. Every interaction, every collision, every flicker of existence leaves a permanent mark in the cosmic record. Information, the detailed blueprint of what things are and how they got that way, must always be preserved. It can be scrambled, hidden, or transformed, but it can never be erased. This principle is called Unitarity, and it is the bedrock of reality at the smallest scales. It means the past always leaves a trail, and the future is always, in principle, predictable from the present. The other book is a sweeping epic of warped space and bent time. This is Einstein's theory of general relativity, which describes the force of gravity not as a pull but as the curvature of the universe's fabric. It tells the story of planets, stars, and galaxies. And within its pages, it allows for the creation of objects so dense, their gravity so absolute, that they punch a hole in the ledger itself, a black hole. According to this rulebook, if something falls into a black hole, it is gone. Its information is trapped behind an invisible boundary called the event horizon, severed from the rest of the universe forever. The geometry of spacetime is deterministic, meaning it follows clear rules, but those rules have no clause for preserving the identity of what falls in. So here we stand with two magnificent, wildly successful theories. One declares information is immortal. The other builds tombs from which information can never escape. For decades, physicists could live with this uneasy truce because these two domains, the quantum small and the gravitational large, rarely had to directly confront one another. But then we placed a black hole, a product of gravity's grand theory, under the microscope of quantum law, and at that terrifying intersection, the two rulebooks began to violently contradict each other. As physicist John Preskill put it, if black holes destroy information, they undermine the foundations of quantum mechanics. This is not a minor accounting error. It is a fundamental crisis, a crack in reality's foundation, and the man who first forced everyone to stare into that crack was Stephen Hawking. Stephen Hawking sat before a daunting mathematical landscape, one where the two rulebooks of the universe finally collided. He was applying the strange rules of the quantum world to the immense gravity of a black hole's edge. His calculation in 1974 produced a result so shocking, it felt like a betrayal of physics itself. Hawking discovered that black holes are not eternal, silent tombs. They glow, they have a temperature, and given enough time, they completely evaporate, fading away into nothing. This glow, now called Hawking radiation, comes from the chaotic quantum sea that exists everywhere, even in empty space. Here, pairs of virtual particles constantly flicker into and out of existence, borrowing energy from the universe before annihilating each other and paying it back. Normally, this dance leaves no trace, but at the very precipice of a black hole's event horizon, the point of no return, gravity warps the rules. One particle of the pair can fall inward, crossing the horizon forever. Its partner, now stranded and real, flies off into space as radiation. To an outside observer, it looks as if the black hole itself is emitting a faint, cold heat. This slow, relentless leak of energy comes at a cost, draining the black hole's mass. Over trillions upon trillions of years, the black hole shrinks, and eventually it vanishes. But Hawking's real bombshell was in the nature of this escaping radiation. He showed it was purely thermal, like the glow from a hot stove. It carries no signature, no fingerprint, no hidden code. The radiation from a black hole that formed from a collapsed star is identical in every quantum detail to the radiation from a black hole that formed from a mountain of old books. All the intricate information about what fell in, the unique arrangement of particles that made a star or a book, is scrambled beyond recovery by the event horizon. When the black hole finally evaporates to a point and winks out of existence, that information has nowhere left to go. According to Hawking's math, it is deleted from the universe. Gone, this was the paradox made terrifyingly real. Quantum mechanics insists information is immortal, a permanent part of reality's ledger. Hawking's calculation, using quantum mechanics itself, now said that black holes are cosmic shredders, permanently erasing that ledger. The universe, it seemed, did have a delete button. Hawking was so convinced by the strength of his own equations that in 1997, he made a famous bet with fellow physicists John Preskill and Kip Thorne. The wager was simple, that information swallowed by a black hole is lost forever. He was betting against the very foundation of quantum theory. For decades, this view held powerful sway, casting a long shadow over theoretical physics. It forced everyone to ask a horrifying question. If black holes can erase reality's past, then is our understanding of cause and effect, of history itself, just an illusion? Hawking's bet sent a shockwave through the foundations of physics because it violated a principle so sacred it was considered unbreakable. To understand why, think of a book tossed into a fire. The pages curl and blacken, the ink vanishes, the physical object is reduced to a pile of ash and a plume of smoke. To any ordinary observer, the story is gone. But the laws of quantum mechanics tell a different tale. In principle, if you could collect every single atom of ash, every wisp of smoke, every photon of light and bit of heat emitted by that fire, and if you had a computer powerful enough to track their impossibly complex interactions, you could run the entire process backward. You could reconstruct the book word for word, letter by letter. The information was not destroyed. It was merely scrambled, transformed into a vastly more complicated form, but it never left the universe. This is the core promise of quantum mechanics, a rule called unitarity. It states that the evolution of any quantum system is reversible. The total amount of quantum information must always be conserved. You can think of it like a cosmic accountant who ensures the books always balance. Every particle has a quantum state, a precise set of probabilities describing its properties. Unitarity guarantees that the sum of all probabilities for what can happen next always equals 1 or 100%. Nothing just disappears from the ledger. This is why the famous thought experiment of Schrödinger's cat is so profound. The cat in the box is in a superposition, both alive and dead, until we look. But the information about which outcome will occur is not lost. It is encoded in the quantum state of the entire system, the atom, the vial, the cat, the box. Observing it simply reveals the answer that was always contained within that intricate web of quantum connections. To lose information, to truly delete it, would be to have probabilities that no longer add up to 1. The cosmic accountant would find a gap in the books, a transaction with no record. As physicist Leonard Susskind powerfully argued, if information can be lost, then causality itself breaks down. The past would no longer reliably determine the future. Physics would become unpredictable, not just in practice but in principle. the very idea of a consistent, logical universe would evaporate. This is why Hawking's conclusion was so revolutionary and so deeply disturbing. He wasn't just proposing a weird property of black holes. He was using the math of quantum mechanics to suggest that quantum mechanics itself had a fatal flaw when faced with gravity's ultimate extreme. It was as if the cosmic accountant had discovered a vault, a black hole where receipts went in and never came out, making the entire financial system of reality unreliable. This terrifying possibility forced physicists into a corner. They had to propose desperate, almost unthinkable solutions. Either our understanding of quantum mechanics was wrong, or our picture of black holes was missing something profound. The hunt for that missing piece would lead to ideas stranger than fiction. Faced with this cosmic crisis, physicists became detectives searching for an escape hatch. They refused to accept that the universe's most fundamental law could simply break, so throughout the 1970s and 80s, they proposed a series of ingenious, often desperate rescue plans. The first line of defense was a subtle hope. Perhaps Hawking was wrong about the radiation being purely thermal. Maybe the information was not destroyed, but instead encoded into the escaping Hawking radiation in an impossibly complex, scrambled form. Think of taking a beautiful, intricate mosaic and shattering it, then tossing the pieces into a hurricane. The image is gone, but if you could track every single fragment through the storm, you could, in theory, reassemble it. This idea suggested black holes were not shredders, but the universe's most chaotic encryption machines. The information was still there in the radiation, but so hopelessly mixed that it was effectively lost to any conceivable observer. While this preserved the letter of the quantum law, it felt deeply unsatisfying. It meant the information, though technically saved, was locked away in a code no one could ever crack, which for all practical purposes was the same as it being gone. As theorist Don Page noted, the sheer complexity involved in such scrambling was staggering, pushing against the very limits of what physics could describe. Another proposal was even stranger, the remnant hypothesis. This idea suggested that a black hole does not evaporate completely to nothing. Instead, the evaporation process halts when it reaches a speck of matter the size of the Planck length, a scale a billion trillion times smaller than an atom. This nearly point-like remnant would then sit there forever, a permanent vault containing all the information that ever fell into the original black hole. But this tiny solution created a massive problem. If such a remnant exists, it must be capable of storing an infinite amount of information, since a black hole of any size could form and eventually shrink down to the same Planck-sized object. This leads to a universe littered with identical-looking specks, each holding the unique history of an entire star or galaxy, creating a paradoxical landscape of infinite possibilities crammed into finite packages. Perhaps the most science fiction-like escape route was the baby universe proposal. Here, the information does not escape back into our cosmos at all. Instead, as a black hole forms and evaporates, it pinches off a new, separate universe from our own, a tiny bubble of space-time connected only by a narrow wormhole. All the information carried by the infalling matter would be funneled into this newborn cosmos, forever inaccessible to us but technically preserved in a new reality. It was a beautiful idea, effectively transferring the data to another hard drive, but it offered no way to test it and felt more like a philosophical relocation of the problem than a true solution. Each of these early defenses was creative, but each came with a heavy cost, either introducing new paradoxes, relying on untestable physics, or making the information so inaccessible it might as well be lost. They were patches on a deepening crack, highlighting just how profound the crisis was. The real answer would not come from adding new objects to the universe, but from radically reimagining the fabric of the universe itself, a shift that would emerge from the most ambitious theory of all, string theory. The resolution to this crisis would not be found by adding new cosmic objects, but by redefining the very nature of space itself. A radical idea began to take shape, one suggesting that our entire perception of a three-dimensional world is a magnificent illusion. This is the holographic principle, and its first clues came from the most unlikely of places, the thermodynamics of a black hole. In the 1970s, physicist Jacob Bekenstein made a startling proposal. He argued that a black hole must have entropy, a measure of the hidden information or disorder within a system. This was a bizarre notion because a black hole, according to classical theory, was the simplest object imaginable, described only by its mass, spin, and charge. It was a cosmic blank slate. Yet Bekenstein and later Hawking showed through elegant mathematics that a black hole's entropy is not proportional to its volume, as you might expect for any normal object. Instead, it is precisely proportional to the surface area of its event horizon. The amount of information a black hole can contain is painted, not within its vast three-dimensional interior, but on its two-dimensional boundary. Think of it like this. Imagine a room filled with furniture, books, and intricate decorations. According to this new logic, all the information needed to describe every object in that three-dimensional space could be completely encoded on the two-dimensional walls enclosing it. The room you experience is a projection, like a three-dimensional movie being played from data stored on a flat screen. This is the essence of a hologram. The shiny security image on your credit card looks three-dimensional with depth and perspective, but all that information is actually stored in the microscopic grooves on the flat plastic surface. Gerard T. Hooft and Leonard Susskind took this black hole insight and made a breathtaking leap. They proposed that the holographic principle might not be a special quirk of black holes, but a fundamental property of our universe. Perhaps all of the information contained within any region of space, from a star system to this very room, is encoded on a distant, enclosing surface. If true, this completely redefines our idea of locality, the notion that objects and information exist at specific points in space. Information does not travel freely in three dimensions. It is stored on a lower dimensional screen, and our rich three-dimensional reality is a kind of cosmic projection, an emergent illusion. For the black hole information paradox, this offered a stunning way out. When an object falls toward a black hole from our outside perspective, it never actually crosses the event horizon. Instead, according to the holographic view, its information is smeared and scrambled across the hot, vibrating membrane of the horizon itself. It is like a fly hitting a window pane and leaving a detailed imprint. The three-dimensional interior of the black hole, with the object seemingly falling forever toward the center, is just a shadow play, a projection of that two-dimensional data. The information never enters a place from which it cannot return. It remains on the surface where it can, in theory, eventually be radiated back out as the black hole evaporates, woven into the fabric of the Hawking radiation. This was the first major conceptual breakthrough that showed information loss might be a profound illusion, a trick of perspective arising from our incomplete understanding of how gravity and quantum information intertwine. The holographic principle pointed toward a deeper, unified theory where space itself is not a fundamental stage, but a secondary construction. And the most successful realization of this radical idea would come from a specific mathematical universe, leading to a discovery that would turn the paradox completely on its head. The holographic principle was a profound insight, but it still felt like a description of the problem rather than a tangible mechanism. We needed a new picture of what a black hole actually is, one built from the ground up using quantum principles. That picture would emerge from the most ambitious attempt to unify all of physics, string theory. Here, the fundamental building blocks of reality are not tiny dots, but unimaginably small, vibrating loops of energy. And when you apply this framework to a black hole, the classic image of a dark, empty pit in space shatters completely. In its place, we get something far stranger, a fuzzball. Imagine the smooth, featureless spacetime of a classical black hole, that perfect mathematical vacuum. Now, replace it with a seething, tangled ball of cosmic yarn. This is the fuzzball conjecture, pioneered by physicist Samir Mathur. In this view, a black hole is not a region of empty space with a point of infinite density at its core. It is a specific, gargantuan configuration of the universe's fundamental strings, packed together at the highest possible density. There is no sharp event horizon as a boundary between something and nothing. Instead, the entire volume of what we thought was the black hole's interior is filled with this intricate, vibrating structure, a quantum hairball of unimaginable complexity. The surface of this fuzzball is where the intense gravity we measure originates, but there is no inside to fall into in the traditional sense. An object approaching it would not sail smoothly through a horizon and into a dark interior. It would collide with and merge into this fuzzy quantum surface, its information instantly becoming part of the fuzzball's intricate vibrational pattern. This solves the paradox at its root by eliminating the very thing that caused it, the information-swallowing singularity. There is no place where information gets trapped and destroyed. Instead, all the data about everything that ever formed the black hole is stored right there, in the quantum mechanical state of the fuzzball itself. Hawking radiation then has a clear physical origin. It doesn't mysteriously appear from empty space at the horizon. It is emitted from the hot, vibrating surface of the fuzzball, much like heat radiates from a glowing coal. And because that radiation comes directly from an object that contains all the original information, it can carry that information away, woven into its subtle quantum correlations. The radiation is not random thermal noise, it is an encrypted broadcast of the black hole's entire history. This represents a monumental shift in perspective. For decades, we thought of black holes as places where something became nothing, where matter was crushed into a silent point. The fuzzball revolution says black holes are not nothing, they are the ultimate something. They are the most complex, information-rich objects in the entire cosmos. They do not delete reality, they are its most densely packed libraries. This alignment with quantum mechanics is elegant, but it comes with a profound and unsettling cost. It forces us to abandon one of the most cherished ideas in all of physics, the principle of locality. But if black holes are fuzzballs, where does an astronaut go? The classical story of general relativity offers a clear, if haunting, answer. As an astronaut drifts toward a massive black hole, they approach the invisible boundary of the event horizon. According to Einstein's equations, crossing this line is an utterly uneventful experience, a moment of no drama. There is no flash of light, no sudden jolt, no physical marker. The curvature of spacetime is smooth, so the astronaut feels nothing special as they pass the point of no return, their fate now sealed by the relentless pull of gravity. This serene picture held for nearly a century, but in 2012, a landmark paper by physicists Ahmed Almary, Donald Marolf, Joseph Polchinski, and James Sully, known by their initials AMPS, dropped a conceptual bomb on this peaceful scene. They argued that to save quantum mechanics from the paradox, to prevent information from being lost or cloned, the event horizon could not be a place of no drama. It must be a wall of fire. Their logic was a devastating trap built from the principles of quantum entanglement. To understand it, picture our astronaut just outside the horizon. According to Hawking's process, pairs of particles are constantly flickering at the edge. One falls in, its partner escapes as radiation. These two particles are entangled, a quantum link that ties their fates together. Now, fast forward a very long time. The black hole has evaporated almost completely. the information about the original astronaut who fell in long ago must now be fully encoded in the Hawking radiation that has been streaming out for eons. For that to be true, a late piece of escaping radiation must be entangled with that early radiation, which holds the astronaut's information. But here is the catastrophic catch. That late radiation particle is also supposed to be entangled with its partner that fell into the black hole long ago. In quantum mechanics, a principle called monogamy of entanglement forbids this. A single particle cannot be fully entangled with two different things at once. It is like a secret that can only be shared with one other person. To preserve the information, the entanglement between the infalling particle and its escaped partner must be severed. And breaking a quantum entanglement bond releases a colossal amount of energy. The result, the AMPS paper argued, is not a smooth horizon. It is a searing curtain of high-energy particles, a firewall that would instantly vaporize any astronaut attempting to cross. Joseph Polchinski framed it as a choice between three intolerable evils. Either information is lost, which destroys quantum mechanics, or information is duplicated, creating forbidden clones, which also destroys quantum mechanics. Or the event horizon is a deadly firewall which destroys general relativity's smooth spacetime. Each option violated a fundamental pillar of physics. The Firewall Paradox did not solve the information problem. It intensified it into a trilemma, proving that even the most promising escape routes led to new, seemingly insurmountable cliffs. It forced everyone to confront an ugly truth, that our basic assumptions about locality and entanglement might be fundamentally flawed when spacetime itself is being generated from quantum information. The only way forward was to question the nature of reality at its most basic level, to ask if space and time are even real, or merely a grand illusion woven from countless quantum threads. Einstein left us with two of his most mysterious gifts. One was a geometric tunnel through space, the other a ghostly link between particles. Decades later, we are discovering they might be the exact same thing. In 1935, Albert Einstein and his colleague Nathan Rosen published a paper exploring a strange consequence of his own equations of gravity. They found that the geometry describing a black hole could, in theory, be extended to form a bridge, a tunnel connecting two distant regions of space. This structure, later called an Einstein-Rosen bridge or a wormhole, offered a tantalizing shortcut through the cosmos, though it was widely believed to be unstable and impassable. In that very same year, Einstein collaborated with Boris Podolsky and Nathan Rosen on a completely different paper, one attacking the strange implications of the new quantum theory. They described a thought experiment where two particles could become so deeply linked that measuring one would instantly determine the state of the other, no matter how far apart they were. Einstein famously called this spooky action at a distance, and he believed it revealed a flaw in quantum mechanics. We now know this phenomenon, called EPR entanglement, is very real. For most of the 20th century, these two ideas, the geometric wormhole, labeled ER, and the quantum entanglement, labeled EPR, lived in separate worlds. One was about the large-scale curvature of spacetime, the other about the invisible connections between the smallest particles. They seemed to have nothing to do with each other. Then, in 2013, a breathtaking conjecture emerged from physicists Juan Maldacena and Leonard Susskind. They proposed a radical equation, ER equals EPR. What if the wormhole and the quantum entanglement are not just analogous, but are two different descriptions of the exact same underlying reality? This idea suggests that what we perceive as spooky action at a distance, a particle here instantly influencing a particle light years away, might have a geometric explanation. The two particles are not communicating faster than light through empty space. Instead, they are connected by a microscopic wormhole, an Einstein-Rosen bridge so tiny it is woven into the quantum foam of spacetime itself. The entanglement is the bridge, For the black hole information paradox, this offers a stunningly elegant escape from the firewall trap. Remember the problem: an astronaut outside sees a deadly wall of fire, while an astronaut falling in experiences a smooth horizon. ER equals EPR suggests both are right because their perspectives are connected by a different geometry. The Hawking radiation particle escaping to the outside and its entangled partner falling into the black hole are not two separate entities. They are the two mouths of a single, complex quantum wormhole. Information does not need to travel across the fiery horizon or be cloned. It simply takes a different path, moving through the wormhole connection that the entanglement itself creates. This makes the event horizon non-local, a concept where points that seem far apart in our classical view of space are actually intimately connected in the deeper quantum geometry. The firewall vanishes because there is no sharp, local boundary to set on fire, only a web of quantum threads. This conjecture merges geometry with information in a way that rewrites our cosmic intuition. It hints that spacetime itself, the very stage upon which the universe plays out, is not a fundamental entity. It is an emergent illusion, a holographic projection woven from countless threads of quantum entanglement. The fabric of reality is not smooth and continuous. It is stitched together by these microscopic bridges, each one representing a quantum connection. The true resolution to the black hole information paradox, then, may not be a new law of physics, but a new understanding of what physics describes. We are not looking at objects in space. We are looking at the entangled relationships that create the idea of space in the first place. The classic picture of a black hole is one of ultimate simplicity, a cosmic object stripped of all identity. For decades, the no-hair theorem stood as a cornerstone of general relativity, declaring that a black hole could be completely described by just three numbers: its mass, its electric charge, and its spin. Everything else, every intricate detail of the star that collapsed or the planets it swallowed, was permanently erased. A black hole, it seemed, was the universe's ultimate bald head. But what if that smooth surface is an illusion hiding a subtle, intricate texture? A new line of thinking suggests black holes are not bald at all. They have quantum hair. This idea, championed by physicists like Andrew Strominger, proposes that when matter falls into a black hole, it does not vanish without a trace. It leaves an imprint on the event horizon itself, not in the form of physical bumps or ridges, but in infinitely subtle, zero-energy excitations of the gravitational and electromagnetic fields. These are called soft hair. Think of the horizon not as a static wall, but as a perfectly still pond. If you drop a single grain of sand into its center, it creates a tiny ripple. That ripple carries information, the energy and direction of the impact. Now imagine the pond's surface is made of spacetime itself. When an object falls in, it creates not a water ripple, but a gravitational or electromagnetic one, a faint, permanent wave frozen on the boundary. These are the soft hairs, an infinite collection of such imprints, each one a delicate record of something that crossed the threshold. The analogy is like throwing a brightly painted ball into a vat of thick, black tar. The ball itself sinks and is lost from view, seemingly gone forever. But look at the surface of the tar. The impact leaves behind a unique splatter pattern, a spray of colored droplets in a specific configuration. That pattern on the two-dimensional surface holds a memory, a fossilized record, of the three-dimensional object that entered. In the same way, the quantum hair on a black hole's horizon is the splatter pattern of infalling matter, a subtle fingerprint encoded in the fabric of gravity and light at the very edge. This challenges the old no-hair theorem not by overthrowing it, but by refining it. Mass, charge, and spin are the coarse, large-scale features, the obvious facts about the black hole. The soft hair is the fine print, the infinite collection of tiny details that preserve the history of its formation. The information is not trapped inside, doomed to be crushed at a singularity. It is stored holographically on the surface, woven into these delicate patterns, and because these patterns are part of the horizon's quantum state, they can, in principle, influence the Hawking radiation that slowly leaks away. As the black hole evaporates, the soft hair gets transferred, bit by quantum bit, into the outgoing radiation, carrying the story of what fell in back out into the universe. This offers a more conservative path to resolving the paradox, one that works within an extended framework of Einstein's classical gravity, suggesting that the tools to save information were hiding in plain sight all along, written in the faintest possible whispers on the edge of darkness. For decades, the information paradox was a war of ideas, fought with thought experiments and philosophical arguments. But science demands more than elegant stories, it demands numbers. It needs a prediction we can calculate and check. The ultimate test would be a graph, a simple line tracking the fate of information across the entire life of a black hole. This is the Page curve, and its recent derivation is perhaps the most concrete evidence we have that reality's ledger remains intact. Imagine plotting the entanglement entropy of the Hawking radiation, a measure of its hidden information, against time. At the very beginning of a black hole's life, the radiation it emits is nearly featureless, random thermal noise. It tells you nothing about what fell in. So, on our graph, the line representing missing information, or entropy, climbs steadily upward. It seems to confirm Hawking's worst fear, that information is being lost, increasing the disorder of the universe. But physicist Don Page proposed a critical turning point. If quantum mechanics is correct and information is preserved, then the black hole cannot hold onto it forever. Once the black hole has evaporated past its halfway point in mass, a moment now called the Page time, the radiation must change. It can no longer be random. It must begin to carry out the intricate quantum data that has been stored, whether on a fuzzball surface or in soft hair or through wormholes. As this encoded information streams out, the puzzle starts to solve itself. The entanglement entropy of the radiation should stop rising, peak, and then begin a steady descent back to zero. When the black hole finally winks out of existence, all the information has been returned to the universe, leaving no gap in the cosmic books. The graph of this process forms a graceful, arching curve, rising and then falling like a single, symmetric wave. For over 40 years, this curve was a hypothesis, a diagram of what should happen if unitarity were saved. The crushing problem was that no one could actually derive this curve from the known laws of gravity and quantum mechanics. Calculating it required understanding the quantum geometry of the black hole interior, the very place where our theories broke down. The Page curve hung in the air, a beautiful goalpost that seemed forever out of reach. Then, in 2019 and 2020, a series of breakthroughs changed everything. Using advanced tools from quantum gravity, particularly a clever mathematical technique called the Replica trick applied to simplified model universes like Jacques-Teitelbaum gravity, physicists like Jeff Pennington and others achieved the impossible. They performed the calculation, and the result was not a line climbing forever into chaos. It was the Page curve rising, turning over, and falling exactly as required. The information was coming back out. This was a monumental shift. It moved the debate from philosophical possibility to quantitative fact within a calculable framework. The derivation shows that quantum gravity itself, when properly understood, builds in the mechanism for information recovery. The peak of the curve, the Page time, marks the moment when the quantum connections threading through the evaporating black hole become dominant, when the wormholes of the ER equals EPR conjecture effectively stitch the information back into the escaping radiation. We are no longer just arguing that information could escape. We now have a mathematical demonstration within a controlled model of precisely how it does. This doesn't mean the puzzle is completely finished. but it provides a dazzling signpost pointing toward a future theory where space-time and information are seamlessly woven into a single, consistent fabric. The curve on the graph is more than a line. It is the signature of a universe that remembers. The invisible threads of quantum entanglement are what stitch the universe together. When two particles become entangled, their fates are linked in a way that defies ordinary distance, creating a bond so intimate that measuring one instantly tells you about the other, no matter how far apart they are. But how do you measure the strength of such a ghostly connection? Physicists use a concept called entanglement entropy. Think of it not as chaos or disorder, but as a precise measure of hidden information, of how much you don't know about one particle because its story is inseparably woven with its partners. If you have two coins that are perfectly correlated, always landing on the same side, their entanglement entropy is high because knowing the state of one tells you everything about the other. This quantum bookkeeping becomes the critical lens for watching the black hole information drama unfold. Picture the quantum fizz at the event horizon, where a pair of entangled particles pops into existence. One falls inward, the other escapes as Hawking radiation. Initially, these two are deeply entangled, but for the information about what fell into the black hole long ago to eventually escape in the radiation, a profound swap must occur. The escaped particle must, over eons, become entangled with the other escaping radiation particles that carry the black hole's historical data. It must sever its old bond to form a new one. This is the delicate, dangerous transfer that the Firewall Paradox highlighted, where breaking entanglement seemed to require a cataclysmic release of energy. So how does the universe perform this swap without creating a cosmic conflagration? The answer lies in watching the entanglement entropy itself, and its journey traces the now famous Page curve. In the black hole's youth, the escaping radiation particles are entangled primarily with their unfortunate partners that fell in. From the perspective of someone outside collecting the radiation, this looks like a growing cloud of random, disconnected noise. The entanglement entropy of the radiation climbs steadily, as if information is being lost into the void. This is the rising slope of the curve, but as quantum gravity theorists like Patrick Hayden have illuminated through the mathematics of quantum information theory, a subtle shift is occurring behind the scenes. The interior of the black hole and the early radiation are not separate realms. They are becoming quantum mechanically connected through the complex geometry of wormholes, the ER equals EPR bridges. At the Page time, the halfway point of evaporation, these background connections become dominant. The entanglement relationships begin to reorganize. The escaped particle no longer has to violently break its bond with its infalling twin. Instead, through the non-local geometry of the emerging wormhole network, its entanglement is transferred. It becomes woven into the broader tapestry of the radiation field that encodes the black hole's memory. From this moment on, each new piece of Hawking radiation carries out a little more of the stored quantum data. Consequently, the entanglement entropy of the radiation stops increasing. It peaks and then begins its graceful descent. As the black hole nears its end, the outside observer finds that the radiation is no longer a random hiss. It is an intricate, correlated message. All the original entanglement has been carefully redistributed, not severed, but reconfigured. When the evaporation finishes, the entropy returns to zero, meaning all the information is now out here, perfectly preserved in the relationships between the radiated particles. The universe has performed a flawless quantum teleportation of data from the horizon's surface to the far reaches of space, using entanglement itself as the transmission medium. This mathematical story shows that information preservation isn't a hopeful add-on. It is the inevitable outcome of the meticulous swapping and strengthening of quantum connections across time. The paradox dissolves when we realize that in quantum gravity, entanglement isn't just a property of particles, it is the currency of reality, and its accounts always balance. The most powerful evidence for this new reality comes from a mathematical universe so precise it acts as a Rosetta Stone for quantum gravity. In 1997, physicist Juan Maldacena discovered a breathtaking duality, a perfect dictionary translating between two seemingly alien worlds. On one side, picture a strange, curved cosmos called anti-de Sitter space. Its geometry is like the interior of an infinite, hyperbolic bowl, where spacetime itself is warped in such a way that its distant boundary acts like a reflective wall. In this universe, gravity operates as described by string theory. On the other side of the dictionary, imagine a flat, ordinary sheet of paper representing that very boundary. Here, there is no gravity at all. Instead, this boundary is governed by a special kind of quantum particle theory called a conformal field theory, or CFT. It is a bustling, complex system of interacting quantum fields, but it exists in one fewer dimension. Maldacena's monumental discovery, known as the AD-SCFT correspondence, proved these two descriptions are not just similar. They are mathematically identical, two completely equivalent languages for describing the exact same physics. This is the holographic principle made exact and calculable. The entire, rich, three-dimensional universe with gravity in the bowl is perfectly encoded, like a cosmic hologram, on the two-dimensional, gravity-free quantum system painted on its boundary wall. For the black hole paradox, this provides an ultimate laboratory. Imagine a black hole sitting in the center of that warped anti-de Sitter space. According to the duality, that black hole, with all its mysterious interior and event horizon, is not an independent object. It is exactly equivalent to a specific, hot, chaotic state of the quantum particles living on the flat boundary. Crucially, on that boundary, the rules are crystal clear. It is a standard quantum system where unitarity reigns supreme. Information is never lost, it simply evolves in complex but always reversible ways. Therefore, anything that happens to the black hole in the interior, including something falling in, must have a precise, information-preserving translation in the boundary quantum theory. If information seemed to vanish into the black hole, it would mean the well-understood quantum theory on the boundary was suddenly breaking its most sacred law, which we know it does not. The duality forces a revolutionary conclusion. In any consistent theory combining gravity and quantum mechanics, information loss in black holes is simply impossible. It is a mirage caused by trying to describe the system in only one of the two languages. This mathematical framework has become the engine for the field's greatest advances. It was within the controlled environment of AD-SCFT that physicists recently performed the landmark calculations to derive the Page curve, showing the entanglement entropy rise and fall exactly as required. It is here that the ER equals EPR conjecture finds its sharpest form, where entangled particles on the boundary can be shown to create emergent wormhole geometry in the interior. This correspondence does not just suggest a resolution to the paradox, it actively builds one, proving that the universe's ledger can remain balanced even in the face of its most extreme phenomena. Reality itself may depend on where you stand. The most unsettling implication of the paradox is the suggestion that there is no single, objective truth about what happens at a black hole. Instead, what you see is determined by your own journey, a principle called black hole complementarity, proposed by physicists Leonard Susskind, Gerard T. Hooft, and Lars Thorlacius. This idea asks us to accept two contradictory stories as simultaneously true. For an astronaut crossing the event horizon, the experience is serene and uneventful. The horizon is not a physical barrier, and they pass smoothly into the interior, their information traveling with them into whatever lies within. From this perspective, nothing special happens at that boundary. Yet, for an observer who remains forever outside, watching from a safe distance, a completely different story unfolds. They never see the astronaut cross. Instead, from their vantage point, the astronaut's information is smeared and scrambled across the hot, vibrating surface of the horizon. It is then slowly re-radiated back out, encoded into the intricate patterns of Hawking radiation over eons. In this outside view, the information never actually enters the black hole at all. Black hole complementarity states that both of these descriptions are physically correct and complete within their own frames of reference. The key is that no single observer can ever access both stories to compare them and find a contradiction. It is like the famous wave-particle duality of quantum mechanics, where an electron can behave as both a spread-out wave and a localized particle. Which property you observe depends entirely on how you choose to measure it. You can never set up an experiment that catches it being both a perfect wave and a perfect particle at the exact same instant. They are complementary aspects of a deeper, more complex reality. This framework was a direct response to the terrifying cloning paradox. If information both crosses the horizon and remains on it, that would create a forbidden duplicate violating quantum mechanics. Complementarity dissolves this by stating the information is not in two places at once in any single objective reality. It is simply described differently by two observers who are forever separated by a causal boundary. The infalling observer has one valid description, the outside observer has another, and the laws of physics ensure they can never meet to argue about whose notebook is right. This was a radical but crucial step, forcing physicists to abandon the classical intuition of a single, God's eye view of the universe. At the quantum gravitational frontier, reality is not a monolithic stage play. It is a collection of consistent perspectives woven together by the rules of quantum mechanics and relativity. While later challenges like the Firewall Paradox would test the limits of this idea, complementarity cemented a profound lesson that our comfortable notions of a single, objective timeline may be a comforting illusion that shatters at the edge of a black hole. Perhaps the most radical solution to the paradox suggests we have been looking at the black hole's heart all wrong. Instead of a chaotic shredder of information, the singularity could act as a cosmic sensor, enforcing a single, elegant quantum outcome. This is the final state proposal put forward by Gary Horowitz and Juan Maldacena. They reimagined the singularity not as a place where physics ends, but as a boundary where a new law begins. In their view, the crushing center of a black hole imposes a specific final boundary condition on the quantum state of everything that falls in. Think of it like a cosmic filter or a predetermined destination. All the intricate quantum information of the collapsing star and anything else that follows is not destroyed upon reaching this point. Instead, it is projected or forced into one particular quantum state that was set at the black hole's birth. This forced projection has a startling consequence. It effectively teleports the information from the infalling matter directly into the Hawking radiation streaming outward. The singularity becomes a kind of quantum teleporter, not a trash compactor. To understand this strange mechanism, we can use the language of quantum circuits. Normally, a quantum state evolves unitarily, like a complex calculation running step by step in a predictable, reversible way. This is the standard quantum computer. In the final state proposal, the black hole adds a bizarre new step post-selection. Imagine running that calculation, but at the very end, you only accept the answer if it matches one specific pre-chosen result. You throw away all other possible outcomes. This post-selection at the singularity breaks the normal, unitary flow of quantum mechanics. It is a non-unitary process, meaning it is not perfectly reversible in the usual way. Yet its proponents argue this break is tightly constrained, happening only at this one extreme location in the universe, and it serves a vital purpose, to preserve the overall consistency of physics by ensuring information escapes. It is a targeted modification of the rules to save a greater principle. While mathematically intriguing, this idea is deeply controversial. It asks us to accept that the fundamental laws of quantum evolution, which work flawlessly everywhere else in the cosmos, are simply different at the center of a black hole. The singularity becomes a lawgiver, not a lawbreaker. For many physicists, this feels like a step too far, an ad hoc fix rather than a natural consequence of a deeper theory. Yet the very existence of such a proposal highlights the profound desperation and creativity this paradox inspires. It shows the lengths to which theorists will go to protect the sanctity of information, even if it means rewriting the rules at the very edge of spacetime itself. The final state hypothesis stands as a monument to an unsettling possibility that to understand the universe's most extreme phenomena, we may need to accept that reality itself operates on different terms in the dark. But all these theories, however elegant, live in the realm of mathematics and mind. The ultimate judge is the cosmos itself. Can we find proof in the sky, a signal that reality's ledger remains unbroken? For decades, this seemed like pure philosophy, a debate forever trapped in theory. Yet today, for the first time in history, we have tools that might let us eavesdrop on the edge of a black hole and listen for the whispers of preserved information. The most promising avenue comes from the ripples in spacetime itself, gravitational waves. When the LIGO Observatory first heard the cosmic chirp of two black holes colliding, it recorded more than just their merger. It captured the final moments of the ringdown, the brief period where the single, newborn black hole settles into its quiet, final form, vibrating like a struck bell. According to Einstein's pure general relativity, this ringdown should be clean and simple, described by just the black hole's final mass and spin, its boldness confirmed. But if quantum hair exists, if soft imprints from the original stars are preserved on the horizon, they could subtly alter the tone of this ring. The gravitational wave signal might carry faint, additional frequencies, tiny echoes of the information that fell in long ago. Detecting such deviations from the classical prediction would be a monumental discovery, a direct observational hint that black holes are not the simple objects we once thought. It would be like listening to a bell and hearing not one pure note but a complex chord, revealing the unique history of the metal from which it was cast. Another potential signal lies in the elusive Hawking radiation itself. While it is far too faint to detect from any astrophysical black hole in the universe today, the principle is key. If the radiation is truly random thermal noise, its spectrum would be perfectly smooth, like the glow from a hot, featureless coal. But if information is being encoded and carried away, that process should impose subtle correlations or deviations from perfect thermality within the radiation. It would be like finding a hidden, intricate pattern woven into the static of a radio signal. While we cannot yet listen to this signal from real black holes, scientists have created analog black holes in laboratories using supercooled fluids or light, where similar quantum effects occur at the event horizon of a sonic or optical trap. Studying these analog systems allows us to test the fundamental principles of how information might behave at such a boundary, providing crucial clues for the astrophysical case. Then there is the colossal puzzle sitting at the heart of our own galaxy, Sagittarius, a star. This supermassive black hole is relatively quiet, but it is surrounded by a swirling disk of gas and stars. The information paradox applies to it just as surely as to any other. If we could ever observe the detailed physics of matter at its very precipice, we might see signatures of quantum effects that hint at how information is processed. Future telescopes, especially those designed to study the extreme gravitational lensing around its shadow, might one day reveal anomalies that challenge the classical no-hair picture. The journey from a terrifying mathematical contradiction to a testable scientific prediction is what makes the black hole information paradox so vital. It is not just a debate about abstract principles, it is a driving force for new technology and observation. Every time a gravitational wave detector is upgraded for greater sensitivity, or a new tabletop experiment is designed to simulate an event horizon, we are building the tools to answer a fundamental question about the nature of reality. We are learning to read the faintest handwriting of the universe, scribbled not on paper, but on the very fabric of space and time. The search for proof continues, turning our gaze upward, listening for the echoes of information in the dark. This crisis in physics reaches far beyond equations and evaporating black holes. It forces us to ask what we even mean when we say something is real. If information is truly indestructible, a permanent part of the cosmic ledger, then what does that say about our own experience of loss, of endings, of time itself? The paradox suggests a startling possibility that nothing truly vanishes. The past is not a fading memory, it is an eternally present record, woven into the very structure of the universe. From this view, the collapse of a star into a black hole is not an erasure, but a transformation, a translation of matter's story into a different, more fundamental language inscribed on the horizon. This challenges our most intuitive feelings about finality. It hints that what we perceive as an ending might be a limitation of our perspective, not a property of reality. This leads directly to one of the oldest debates in science and philosophy, the tension between determinism and true randomness. A universe that preserves all information in principle could be seen as a cosmic clockwork, where every future state is mathematically determined by the past. There is no deletion, only rearrangement, yet quantum mechanics is built on probability, on genuine unpredictability at its core. The paradox lies in the space between these ideas, suggesting that perhaps the universe is both determined and free in a way we cannot yet comprehend, its certainty preserved not in particles' paths, but in the unbreakable web of their quantum relationships. This information preservation is also intimately tied to the arrow of time, the reason we remember yesterday but not tomorrow. Thermodynamics tells us that entropy, or disorder, always increases, and this gives time its direction. The page curve, with its rise and fall of entanglement entropy, mirrors this cosmic story. The apparent loss of information as the black hole forms corresponds to increasing entropy, the familiar march of time. But the curve's eventual turnaround and descent shows that, from the universe's deepest perspective, this increase is not absolute. It is a temporary, localized phenomenon. The ultimate preservation of information suggests that time's arrow, while overwhelmingly real in our daily lives, might not be a fundamental feature of the cosmos, but an emergent property of how we, as complex systems within it, process information. Then there is the holographic principle's profound challenge to physical existence. If our rich, three-dimensional world of mountains, oceans, and stars is a projection from a two-dimensional surface of encoded data, then what are we? Are we the three-dimensional projection, or are we the data? It suggests that solidity, tangibility, and volume are not primary qualities. They are a user interface, a magnificent illusion generated by quantum information processing on a distant boundary we cannot see. As physicist Carlo Rovelli has reflected, the world is not a collection of things but a network of events, of relationships. The black hole paradox pushes this idea to the extreme, indicating that what we call a thing, even a black hole, is just a temporary knot in that network, a particular configuration of informational relationships. This journey, therefore, is not merely about solving a physics problem. It is about understanding the bedrock of existence. The paradox pushes us to the boundary between physics and metaphysics, asking if reality is ultimately computable, a vast calculation unfolding, and if so, what is running the code? Is the universe simply a consistent, self-verifying set of information relationships where the only real things are the logical connections between them? The black hole, once a symbol of ultimate oblivion, has become our most powerful lens for examining these questions. Its dark silence may not be an end, but an invitation to listen more closely to the subtle, persistent hum of information that structures everything we know. The idea that the universe might forget is a fear as old as physics itself. To see the true weight of Hawking's paradox, we must step back into a time when the cosmos was viewed as a magnificent, predictable machine. In the early 19th century, the French mathematician and astronomer Pierre-Simon Laplace envisioned a being of supreme intellect, now called Laplace's demon. This entity, if it knew the precise position and momentum of every single particle in the universe at one moment, could use the laws of Newtonian physics to calculate the entire future and past of the cosmos. It was a vision of absolute determinism, a clockwork reality where nothing was random and nothing was ever truly lost. Information about the state of the universe was perfectly preserved in its motion, allowing for perfect prediction. This was a universe that never forgot, a cosmic ledger written in stone. But then came a revolution born from steam and industry, thermodynamics. Scientists like Rudolf Clausius and Ludwig Boltzmann introduced a new, unsettling concept, entropy. They showed that in any closed system, disorder tends to increase over time. A drop of ink disperses in water, a hot cup of coffee cools to room temperature, and you can never perfectly reverse these processes to recover the initial, ordered state. From a statistical perspective, information about the original configuration seemed to be lost, swallowed by randomness. The universe, it appeared, could forget after all, not through destruction, but through overwhelming confusion. This introduced a fundamental tension between the microscopic world of particles governed by reversible Newtonian laws and the macroscopic world of experience where time had a clear, irreversible direction. The next great upheaval, quantum mechanics, initially seemed to restore order to the ledger. While it introduced fundamental probability, its core mathematical principle, unitarity, guaranteed that quantum information is never destroyed, only transformed. The cosmic accounting was saved, but now it was probabilistic. Meanwhile, Albert Einstein's theory of general relativity painted gravity as the geometry of spacetime, a beautifully deterministic framework where the future curvature is dictated by the mass and energy present. For a time, these two pillars, quantum unitarity and geometric determinism, could coexist because they governed different realms. The crisis was brewing unseen. General relativity allowed for the creation of black holes, and within them, points of infinite density called singularities, where its own equations broke down. At a singularity, all paths of matter and light simply end. Predictability, the very heart of Laplace's dream, ceased. The stage was now set. You had a quantum theory demanding information preservation, and a gravitational theory that created tombs where information paths terminated. Stephen Hawking's calculation in 1974 was the explosive collision of these two historical rivers. He applied quantum rules to the gravitational edge of a black hole and found that not only could the black hole evaporate, but the information about what fell in seemed to be permanently erased in the process. Hawking was not creating a paradox from nothing. He was revealing the catastrophic fault line where 2 centuries of scientific thought, the unyielding determinism of Laplace, and the unwavering preservation of quantum information finally met and shattered against the dark, absolute reality of the event horizon. This historical arc shows us the black hole information paradox is not a quirky puzzle. It is the latest, most severe symptom of a deep and ancient question. Does the universe keep a perfect record of its past, or is forgetting an essential part of its nature? The equations that resolve this paradox are as beautiful as they are strange. To truly grasp how physicists proved information is saved, we need to peer into their mathematical workshop, where the tools are not wrenches and rulers, but imaginary time and replicated universes. The central challenge was calculating entanglement entropy, that precise measure of hidden information. How do you quantify the ghostly links between a black hole and its radiation? The answer came from a clever sleight of hand known as the replica trick. Instead of trying to compute the entropy directly, which is notoriously difficult, mathematicians found a backdoor. They ask us to imagine not one universe but many identical copies of the same cosmic scenario, say, 4 or 5 replicas of the evaporating black hole and its surrounding space. The trick is to then mathematically stitch these replica universes together in a specific cyclic pattern, like linking the pages of a book into a continuous loop. By performing calculations in this stitched-together, multi-sheeted geometry and then carefully analyzing how the result behaves as the number of replicas approaches 1, you can indirectly extract the entanglement entropy you could not find directly. It is a bit like wanting to know the weight of a single, fragile snowflake. Instead of trying to weigh it on a scale that would crush it, you pack a massive, precise number of identical snowflakes into a snowball, weigh that, and then use the total to deduce the weight of one. To make this replica trick work in a universe with gravity, you need a way to describe all possible quantum histories of spacetime itself. This is where another profound tool enters, the Euclidean path integral. In our everyday experience, time is a real number flowing forward in one direction. But in this mathematical framework, time is treated as an imaginary number, a rotation by 90 degrees into a different dimension. This transforms the familiar timeline of cause and effect into a kind of spatial geometry, a frozen landscape of possibilities. In this imaginary time or Euclidean picture, a black hole is not a dynamic object with an event horizon. It becomes a smooth, donut-shaped surface, a gravitational instanton. Hawking's great insight was that by applying this Euclidean tool to the region around a black hole's event horizon, the phenomenon of radiation naturally emerges from the geometry. The path integral itself is a sum over every conceivable history, every possible path a particle or a spacetime geometry could take. Of course, you cannot literally add up an infinite number of possibilities. So physicists use a powerful shortcut, the saddle point approximation. You find the most probable dominant path, the one with the least action, and calculate its contribution in detail. For a black hole, the dominant classical geometry is the smooth, curved spacetime described by Einstein. But when calculating entanglement entropy using the replica trick, the dominant saddle point geometry is not a single, simple universe. It is a complex, connected spacetime where the replica sheets are joined by wormholes, Einstein-Rosen bridges. These wormholes in the calculation are not science fiction. They are the mathematical manifestation of the quantum entanglement between different parts of the system. Their appearance in the saddle point is how the mathematics naturally builds in the ER equals EPR connection, showing that the information recovery is not an added feature, but an inevitable outcome of the sum over all quantum gravitational histories. The most recent and rigorous advances in this field are formalizing these ideas using the language of operator algebras, specifically von Neumann algebras. This is deep mathematics that classifies the types of observables and information accessible to different observers, like someone falling into a black hole versus someone staying outside. These algebras provide a strict framework to prove that while perspectives may differ, as in black hole complementarity, no fundamental laws like unitarity are broken. The information is always accounted for in the complete quantum description. While the details are intensely technical, the takeaway is powerful. The solution to the black hole information paradox is not just a compelling story or a philosophical argument. It is a result that can be, and has been, derived from first principles using a sophisticated fusion of geometry, quantum field theory, and information science. The page curve is not a wishful graph. It is the output of a calculation in a theory of quantum gravity, a line that emerges from the meticulous sewing of replica wormholes in the path integral over spacetime geometries. This mathematical machinery is the engine of credibility, turning a paradox that once threatened to unravel physics into a guiding light toward a deeper, unified understanding of reality. Yet for all this elegant mathematics, a chorus of respected voices urges caution. Science at its best thrives on dissent, and the black hole information paradox is no exception. Some of the sharpest minds in physics remain unconvinced that the puzzle is truly solved. They argue we may be celebrating a victory in a model universe, while the real cosmic war rages on. Sir Roger Penrose, a titan of gravitational physics, has long held a different view. He finds the notion of information escaping from a black hole to be deeply problematic, suggesting instead that the paradox points toward a necessary incompleteness in quantum mechanics itself. In his conformal cyclic cosmology, the information loss is not a bug, but a feature, a cosmic reset that allows for a new universe to be born from the ashes of the old. For Penrose, the attempt to preserve information at all costs might be forcing quantum theory into a role it was never meant to play when gravity becomes supreme. Other critics focus on the fine print of the solutions we have. The dazzling successes, like the derivation of the page curve, were achieved within highly simplified mathematical universes, particularly the warped, bowl-like geometry of anti-de Sitter space. This ADS setting has a crucial property. Its spatial boundary acts like a reflective wall, keeping everything contained and making calculations tractable. But our observable universe is not like that. We live in what cosmologists call asymptotically flat space, an expanding cosmos where radiation and information can stream away to infinity, never to return. The concern, voiced by physicists like Sabine Hossenfelder, is that the beautiful results from ADS may not smoothly translate to our reality. The mechanisms that work so perfectly in that controlled mathematical lab, the replica wormholes and the precise holographic encoding, might break down or become ambiguous when applied to a real, evaporating black hole sitting alone in the vastness of our flat universe. Are we building a magnificent theory for a cosmos that does not exist? A more philosophical objection cuts to the heart of what information even means. Suppose, for argument's sake, that the quantum data is technically preserved in the Hawking radiation. The mathematics says it is there, encoded in correlations so complex they are effectively encrypted for all of time. Some theorists question whether information recovered in such a form, inaccessible to any conceivable observer within the lifetime of the universe, can be said to be preserved in any physically meaningful sense. If you lock a secret in a vault and throw the key into a star, is the secret still part of the usable world? This line of thinking suggests that even if unitarity is saved in principle, we may have to accept a form of effective information loss, a practical erasure that forever removes events from the causal story of our observable cosmos. The universe's ledger might balance in a hidden accounting dimension, leaving our local reality permanently scarred by loss. These criticisms are not signs of failure, they are the engine of scientific progress. They force proponents of the mainstream solutions to sharpen their arguments, to extend their calculations beyond idealizations, and to confront the messy, asymmetric nature of the real cosmos. As physicist Steve Giddings has noted, the paradox pushes us toward a deeper theory of quantum gravity that must be able to make sense in our universe, not just in a tidy mathematical toy model. The ongoing debate keeps the mystery vibrantly alive, a reminder that our understanding of reality is always provisional. the final chapter on black holes and information is not yet written. The most profound lesson may still be waiting in the dark, ready to surprise us with an answer more strange and wonderful than any we have yet dared to imagine. But if the paradox can be contained to black holes, what about the universe as a whole? Our cosmic home is not static, it is expanding, and that expansion is accelerating. This creates a horizon for our entire observable universe, a boundary beyond which light from distant galaxies will never reach us, not because it is trapped by gravity, but because the space between us is stretching faster than light can travel. This cosmological horizon shares a profound similarity with a black hole's event horizon. And just as Hawking showed for black holes, Stephen Hawking and Gary Gibbons demonstrated that a cosmological horizon should also glow with a faint thermal radiation. This Gibbons-Hawking radiation is not something we can ever hope to detect, as it is drowned out by every other source of energy in the cosmos, but its theoretical existence raises a terrifying question. If our accelerating universe has a horizon that emits thermal radiation, does it also destroy information? Could the ultimate fate of everything we know be not a fiery crunch or a frozen fade, but a slow cosmic deletion? Think of it as the ultimate census. Every star, every planet, every living thing, every moment of history in our observable universe contributes to a vast ledger of information. As the expansion accelerates, more and more of that ledger slips beyond the cosmological horizon, carried away by galaxies receding into unreachable darkness. From our perspective inside this cosmic bubble, that information is effectively lost. It crosses a point of no return, just like matter falling into a black hole. If the radiation from our cosmic horizon is truly thermal and random, carrying no data about what vanished beyond it, then the universe itself is the ultimate information shredder, and the paradox becomes a universal condition, not a black hole anomaly. This bleak possibility forces some theorists to consider even stranger ideas. One speculative but compelling notion is that our entire universe might be the interior of a black hole existing in a larger parent universe. In this view, the Big Bang was not a singular beginning of everything, but the violent birth of a new space-time region from the collapse of matter elsewhere. If true, then our cosmological horizon is not fundamentally different from a black hole's event horizon, just viewed from the inside. The information paradox then becomes recursive, a nesting doll of mysteries. The information from our universe might be encoded on our horizon, which is itself the interior of a black hole in another universe, whose information faces its own paradoxical fate. This perspective dramatically expands the stakes. Solving the black hole information paradox is no longer an isolated exercise in theoretical physics, a puzzle about exotic objects in distant space. It becomes the essential key to understanding quantum gravity on all scales, from the microscopic weave of spacetime to the ultimate fate of the cosmos itself. The fate of information is inextricably linked to the fate of everything. It asks whether the universe keeps a permanent record of its own story, or if the final page of cosmic history is simply blank thermal noise, a silent hum in an infinite, forgetful dark. The search for an answer is not just about saving quantum mechanics. It is about determining whether the cosmos has a memory and whether anything we do or are ultimately matters in the grand, accelerating scheme of reality. These abstract ideas become clearer when we translate them into the language of everyday experience. To grasp how information might survive a black hole, we can use two powerful analogies, each revealing a different facet of the mystery. First, picture a vast, chaotic library. In the classical view of a black hole, this library has a giant incinerator in its basement. When books representing information are thrown in, they burn to ash and smoke, gone forever. The story is erased, but the quantum gravitational view tells a very different tale. Imagine that as each book is tossed toward the incinerator, a superhuman librarian instantly scans every single page, every word, every ink molecule. This librarian then prints the entire contents not on paper, but in a hyper-dense, scrambled code directly onto the walls and ceiling of the library's entrance hall, which represents the event horizon. The book itself may seem to vanish into the pit, but its complete data is now stored holographically on the boundary. Later, as the library itself grows warm, that heat begins to radiate outward. And in that radiating warmth, the super-librarian's process runs in reverse, using the code on the walls to meticulously reassemble the book, page by page, letter by letter, into the air outside. The information was never destroyed, it was translated, stored, and then broadcast. Our second analogy moves from libraries to technology. Think of a black hole as the universe's most secure, super-encrypted thumb drive. When you first connect it and try to read data slowly, bit by bit, it seems completely corrupted. All you get is random, thermal static, like the early Hawking radiation. It appears as if the files have been irreversibly scrambled, but this is because you are trying to read it with the wrong key, using only the classical rules of gravity. The full decryption key is quantum mechanical, and it only becomes usable after you have read exactly half of the drive's total data, a moment mirroring the page time. Once you pass that midpoint, you now possess enough of the output to apply the correct quantum decryption algorithm. Suddenly, the static resolves. The random noise reveals itself as a perfect, ordered signal, and you can recover the original files in their entirety. The data was always there, just locked in a code that required patience and the right perspective to crack. Of course, these are metaphors, and like all metaphors, they have limits. The universe does not literally have a librarian or use encryption software, but these mental models serve a vital purpose. They build a bridge between the cold, abstract mathematics of replica wormholes and entanglement entropy and our human intuition. They help us visualize a process where preservation does not mean things stay the same, but that they undergo a radical, non-local transformation. By making the seemingly paradoxical feel possible, these analogies do more than just explain. They prepare us for the next, even more profound question. If the universe really operates this way, if information is this indestructible and reality is this deeply interconnected, what does that mean for the nature of existence itself? How does it reshape our understanding of what is real? The same quantum scrambling that seemed to erase reality on a black hole horizon is now guiding engineers who build the machines of tomorrow. This paradox has become a powerful lens for a field that seems galaxies apart from astrophysics, the quest to build a practical quantum computer. At the heart of both challenges lies the delicate, fragile nature of quantum information. In a quantum computer, data is stored in qubits, which can exist in superpositions of 0 and 1. But these states are exquisitely sensitive, easily corrupted by the slightest interaction with the outside world, a process called decoherence. To protect this data, scientists use a technique called quantum error correction. The core idea is counterintuitive. You do not hide the information, you spread it out. You encode the data of one logical qubit across the entangled state of many physical qubits. In this way, the information is no longer stored in any single place. It is delocalized, woven into the relationships between all the parts. If one qubit fails or is disturbed, the original data is not lost because it is safeguarded by the collective pattern of the whole. This is a direct parallel to the holographic principle. Just as the information about a three-dimensional star is not stored in its vanished volume but is smeared across the two-dimensional surface of the event horizon, the information in a quantum computer is not in one physical component, but in the holistic entanglement of the entire system. The black hole, in this light, is not destroying information. it is performing the universe's most extreme form of quantum error correction, encoding data across the fundamental qubits of spacetime itself. This connection was made stunningly explicit by physicists Patrick Hayden and John Preskill. They formulated a protocol that treats a black hole like the ultimate quantum computer. Imagine you have a secret message, a piece of quantum information you want to hide. You throw it into a black hole. According to their calculations, the black hole does not lock it away forever. Instead, it scrambles the information with all the other data it contains and begins to radiate it back out with astonishing speed. Hayden and Preskill showed that after a remarkably short time, just the black hole's light crossing time multiplied by the logarithm of its entropy, the information is effectively returned. An outside observer who captures both the early Hawking radiation and the new radiation emitted after the secret was tossed can, in principle, decode the message. The black hole has acted as the fastest possible information scrambler, a process now known as fast scrambling. This is not a flaw, it is a feature, a model of optimal information processing. For quantum computing, this is a revelation. It tells engineers that to protect and retrieve information in a complex, noisy system, you might need to deliberately scramble it first to spread its essence across the entire network, just as a black hole does across its horizon. The dynamics of quantum chaos on that horizon are providing blueprints for managing chaos in our own quantum machines. This cross-pollination is transforming the paradox from a purely theoretical crisis into a wellspring of practical insight. Researchers are now using the mathematical tools developed for black holes, like the Replica trick and the analysis of entanglement entropy, to understand error thresholds and stability in quantum computing architectures. The universe's most mysterious objects are teaching us how to build the technology that could one day unlock new forms of medicine, materials science, and encryption. The line between the cosmos and the computer lab is blurring, revealing that the same fundamental laws that govern the fate of stars also govern the flow of information in our own creations. This tangible link elevates the black hole information paradox from a philosophical puzzle to a central drama in the unfolding story of the quantum age, where understanding the edge of space may be the key to mastering the power of information here on Earth. Perhaps the most poetic escape route for information is also the most extreme. If the data cannot be erased and cannot remain here, then perhaps it simply moves to a new address in a reality next door. This is the baby universe hypothesis, where a black hole's collapse does not create a dead-end singularity, but a doorway. In this breathtaking speculation, the immense gravitational crunch at a black hole's core becomes the big bang of an entirely new cosmos, budding off from our own like a bubble on the surface of an infinite ocean. The information carried by the star and everything else that fell in is not destroyed, it is evacuated. It becomes the foundational seed for a new spacetime with its own laws, its own history, and its own future, forever separated from our causal reach. For our universe, the information is as good as gone, having crossed a one-way border into an unreachable beyond. Yet, in the grand multiversal ledger, it persists. This idea finds a powerful echo in the theory of eternal inflation, which paints our cosmos not as a lone island, but as one bubble in a frothing, endless sea of false vacuum. In this eternal sea, new bubble universes are constantly nucleating, each with its own random set of physical constants. The physicist Lee Smolin took this a step further with his fecund universes hypothesis. He proposed that every black hole collapse in our universe is the birth of a new one. Furthermore, the laws of physics in that baby universe might be slightly mutated from our own, perhaps tuned in a way that makes black hole formation more likely. In this stunning vision, cosmic evolution operates by natural selection across universes, with universes that produce more black holes giving birth to more offspring. Information is the genetic code passed from parent to child, preserved in the very structure of the new reality. While philosophically captivating, this solution walks a fine line between resolution and elegant evasion. It saves the principle of information preservation but does so by declaring the problem permanently out of bounds. It is akin to a librarian, unable to find a misplaced book in the stacks, declaring it has been moved to a library in another country that we can never visit. The local ledger shows a loss, but a global, unverifiable account insists it is balanced. For all practical purposes within our cosmic bubble, information has vanished, and physics must grapple with that observable consequence. Yet, the idea's true value lies in the sheer scale of imagination it demands. The black hole information paradox becomes a key that does not just unlock a door within our universe, but suggests the existence of an entire mansion of realities we have yet to perceive. It forces us to consider that the answer may not be found by looking deeper into the hole, but by realizing the hole is a tunnel to somewhere else entirely. The equations of quantum gravity have reshaped our stories of the cosmos. This profound mystery has long since escaped the pages of academic journals, igniting the public imagination and reshaping the very myths we tell about reality. Science fiction, always a mirror to our scientific anxieties, has eagerly woven the paradox into its narratives. The film Interstellar presents a stunning visual translation, where the protagonist navigates a tesseract inside a black hole, a higher dimensional library built from his daughter's memories. Here, the they who built it are future humans who have mastered gravity, and the crucial data that saves humanity is not pulled from a singularity, but is sent back as quantum information, a tactile message across the fabric of spacetime. It is a cinematic metaphor for the universe's potential to preserve and communicate its own history, even from beyond the point of no return. Similarly, Cixin Liu's monumental novel The Three-Body Problem and its sequels use advanced physics, including concepts of information preservation and higher dimensional warfare, not as backdrop but as the central driver of cosmic sociology and conflict. These stories do more than entertain, they serve as public thought experiments, allowing millions to grapple with the implications of a universe that might never forget. The paradox's core phrase, "information is never lost," has itself escaped into the wild. It has become a resonant meme in technology and philosophy circles, a shorthand for digital permanence in an age of cloud storage and blockchain, and a philosophical anchor in debates about consciousness and legacy. It speaks to a deep, almost primal human tension between our longing for permanence and our intimate experience of impermanence. We watch memories fade, civilizations fall, and stars burn out, yet this scientific idea whispers that nothing is truly gone, only transformed. This cultural resonance was fueled by the public faces of the debate. Stephen Hawking's iconic lectures, delivered through his speech synthesizer, turned the terrifying prospect of cosmic deletion into a gripping human drama. Leonard Susskind's passionate, publicly accessible battles with Hawking over the fate of information were not private academic disputes. They were performed on a global stage, transforming complex tensor calculus into a compelling story about the soul of physics itself. These thinkers became modern-day mythmakers, translating the universe's most obscure rules into narratives about fate, memory, and existence. This journey from dense equations to blockbuster plots and coffee shop philosophy is a powerful testament. It reveals that the black hole information paradox is not merely a technical problem to be solved by physicists. It is a fundamental question that echoes our oldest wonderings. Every culture has myths about what endures after death, what traces we leave on the world, and whether the past is truly fixed or can be rewritten. The paradox modernizes these eternal questions, framing them not in terms of spirits or gods, but in the immutable language of quantum bits and holographic screens. It shows that at its frontier, science does not leave storytelling behind. It generates new, potent myths for a technological age. the black hole, once a symbol of pure annihilation, has been culturally reinvented. It is now also a potential vault, a transmitter, a cosmic computer, or a doorway. This cultural absorption proves the idea touches a universal nerve. We are all, in a sense, trying to understand whether our stories are etched into the universe or merely written on water, destined to vanish without a trace. The paradox assures us that the cosmos itself might be keeping the ledger. At the very heart of the black hole, where all paths of matter converge, lies the ultimate enigma, the singularity. This is the point where the curvature of spacetime becomes infinite, where the elegant equations of general relativity scream in protest and simply stop providing answers. It is the classical place where reality, as we understand it, dies, and it is here, at this final frontier, that all our clever solutions to the information paradox face their greatest test. Every resolution we have explored, from fuzzballs and firewalls to holographic screens and wormholes, shares a common strategy. They build a protective barrier. They effectively screen off the singularity, preventing information from ever reaching that point of infinite density and geometric nonsense. The fuzzball fills the interior with quantum structure. The holographic principle stores data on the horizon's surface. The ER equals EPR conjecture connects points with wormholes before a singularity can form. These are brilliant workarounds, but they are, in a sense, cosmic architecture designed to avoid the central problem. They tell us what happens instead of a singularity, not what a singularity truly is within a complete theory. This reveals a profound truth. The black hole information paradox will not be fully settled until we possess a complete theory of quantum gravity, a framework that seamlessly marries the warped geometry of Einstein's cosmos with the probabilistic rules of the quantum world. We need a theory that does not break down, a set of laws that can describe the universe's most extreme conditions without flinching. Some promising paths are already being charted. One major contender, loop quantum gravity, approaches spacetime not as a smooth continuum, but as a fabric woven from discrete, finite loops. In this picture, the crushing gravitational collapse of a star does not culminate in an infinitely dense point. Instead, the immense pressure triggers a quantum bounce, a reversal where spacetime itself rebounds. The collapsing matter reaches a maximum density, governed by quantum effects, and then expands outward again, potentially into a new region of spacetime. This idea transforms the black hole singularity from a deadly end into a cosmic transition, a bridge to another phase. If such a bounce occurs, information would not be destroyed. It would be carried through the transition, preserved in the reshuffled geometry of the rebounding universe. This aligns beautifully with the demand for unitarity, offering another mechanism where the cosmic ledger remains balanced. Other approaches, like string theory's landscape and the holographic AD-SCFT correspondence, provide powerful mathematical arenas where information preservation can be proven, yet they often rely on specific, idealized settings. The challenge is to extract universal principles from these models that apply to the messy, asymmetric black holes in our real, expanding universe. The crucial point is this: while the weight of evidence and elegant mathematics now strongly suggests information is preserved, the final chapter cannot be written by half a theory. General relativity gives us the stage, quantum mechanics provides the actors, but we still lack the unified script that directs the play at its most dramatic moment. The singularity remains the locked room at the center of the mystery. We have deduced what must be happening outside, we have heard the sounds through the door, and we have compelling reasons to believe the room is not a tomb. But until we have the full key, the complete theory of quantum gravity, we cannot open that door and see for ourselves. This acknowledgement is not a failure, it is the engine of science. It keeps the story dynamic, honest, and thrilling. The unresolved tension at the singularity is a beacon, calling the next generation of physicists to the final merger of the very large and the very small, where the true nature of reality will ultimately be revealed. The journey began with a terrifying claim that black holes could erase the past. Stephen Hawking's calculations suggested these cosmic objects were not just dark but forgetful, emitting a formless thermal glow that carried no memory of what created them. This was the paradox in its rawest form, a direct challenge to the universe's most sacred ledger. From that alarming starting point, we ventured into the landscape of possible escapes. We explored the holographic principle, which reimagined the black hole's entire three-dimensional volume as a projection from a two-dimensional surface, a cosmic movie screen where information could be painted and preserved. We met the Fuzzball, a tangle of fundamental strings that replaced the empty pit with a seething, information-rich quantum structure, eliminating the destructive singularity entirely. Each idea was a step away from the classical picture of oblivion. Then came the crisis. The Firewall Paradox forced a brutal choice, presenting a trilemma where saving information seemed to require violating other fundamental laws, either by creating deadly walls of energy or forbidden clones of quantum data. It was a moment of profound frustration, revealing that patching one hole in reality might tear another. The breakthrough arrived from a radical synthesis. The equation ER equals EPR proposed that the geometric tunnels of wormholes and the ghostly links of quantum entanglement were not just similar, they were the same phenomenon described in two different languages. This merged gravity with information at their deepest roots. It was joined by the concept of quantum hair, the idea that infinitely subtle imprints on the event horizon could record a falling object's passage, and by the monumental derivation of the page curve, a graph calculated from quantum gravity itself that showed the entanglement entropy of Hawking radiation rising, peaking, and falling exactly as required for information to return. The emerging consensus from these threads is stunningly elegant. Information is not lost inside a black hole. It is preserved through the intricate, non-local geometry of spacetime itself, a geometry woven from quantum entanglement. Black holes are not tombs, they are transformers, or perhaps the universe's most extreme encryption and decryption devices. They take the complex quantum information of a star and translate it, storing it holographically on their horizon, and then slowly broadcasting it back out, woven into the correlations of the radiation they emit. The key lesson unifying all this work is that spacetime and quantum information are not separate entities. They are two sides of a single coin. Spacetime may not be the fundamental stage upon which physics plays out. It might be an emergent illusion, a three-dimensional image generated by the quantum information relationships of a deeper, two-dimensional reality. Viewed from this unified perspective, the black hole information paradox was not a sign that physics was broken. It was a necessary growing pain, a brilliant flare of contradiction that forced us to look beyond our comfortable, separate theories. It guided us kicking and screaming toward a deeper understanding where the death of reality is an illusion. Nothing truly vanishes. When a star collapses, when matter crosses the event horizon, it is not deleted. The information simply changes form, moving from the language of particles and forces into the language of geometry and entanglement, becoming part of the very fabric from which space and time are knitted. This synthesis resolves the crisis not by choosing one rulebook over the other, but by showing us that both books were always chapters in a grander, unified story we are only now beginning to read. We have traversed the event horizon of thought, exploring a paradox that questions whether the universe remembers. From Hawking's radical proposal to the elegant dance of holography and entanglement, the journey reveals a cosmos that is far more resilient and interconnected than we imagined. The prevailing answer to the question of where reality goes when it dies is increasingly clear. It does not die at all. information, the bedrock of reality, is preserved, scrambled, and ultimately redeemed through the quantum mechanics of spacetime itself. This resolution reaffirms the power of scientific inquiry to confront even the most bewildering mysteries. As we stand on the brink of a theory of quantum gravity, let this paradox remind us that reality is not what it seems, and in seeking to understand the darkest corners of the universe, we ultimately illuminate the nature of existence itself. If this exploration reshaped your view of reality, share your thoughts below and subscribe for more journeys to the edge of understanding.